Hey y'all, this is a recording of practice test 2 for Stats 309, and we will go over this again during the review session on Thursday night. But if you want to look over this before or you can't come to the review session, this is a quick review. So the first thing you need to do for your test is to download the test2practice.r data into your R. So we're just going to download this practice data. Then you go to your R script, you hit File, Open File, and it would be in your downloads, and hit Open. And then it asks if you want to load the data into the environment, and hit Yes. So then this grades data file, the ci.prop function, and the ztest.p function are automatically loaded in for you to use on your exam. So that's the only thing you need to do with data. So now let's go to the questions. So question 2 says a granola bar company decides to do some market research by stationing several of their employees inside Whole Foods to ask customers in the granola bar aisle their opinions of the product and their competitors' products. So all the options are invalid. We just have to pick why this is an invalid way to sample customers. So we know that, we know that this is invalid because picking only Whole Foods customers isn't going to be a representative sample. This first option is saying that we have to take a census, and that's not true. You don't have to take a census to get a representative sample. B says it's impossible to get a large enough sample using this approach. Yes, you can get a large enough sample using this approach. Plenty of people are going to be shopping at Whole Foods. So C is the correct answer. It's invalid because the sample will not be representative of all potential customers of these granola bars. So question 2 is that. Question 3. A recent poll surveyed 642 voters for the Virginia governor's race found that Northam is projected to get 48% of the vote. Based on a 95% confidence interval, which of these outcomes would be surprising? So for this question, it wants you to make a confidence interval and see what the confidence interval is for a proportion of 48% and a sample size of 642. So you have that ci.prop function, and we always put our p hat, then our n, and then our confidence level. This defaults to 0.95. So if it makes you feel better, you can put confidence level equals 0.95. If you're also looking for a 95% confidence interval, you don't have to put it, and it will default to 0.95. So you can see this gives you the exact same answer as this because the function defaults to 0.95. If you wanted a different confidence level, you could put 0.9 for 90%, you could put 0.99 for 99%. We just want 0.95, so I'm going to leave it like that. So this is our confidence interval for 95% for this proportion, this sample size. So we see that 54% is outside of it, 48% is inside, 45% is inside, 51% is inside. So the only one that is surprising is the one that is outside of that 95% confidence interval. Question 4. An Olympic archer is able to hit the bullseye 81% of the time. Assume each shot is independent of the others. She shoots 12 arrows. Is the number of bullseyes that she hits a binomial random variable? So we have 4 conditions for binomial random variables, and you'll just write these on your cheat sheet, and you'll have them if you need to reference them, and writing them down is going to help you remember them. So the trials have to be independent, which this question said each shot is independent. The chance of success is the same each time, which it said it's 81%. There can only be 2 outcomes, success and failure. And this is because she either hits the bullseye or she doesn't hit the bullseye. And it's a fixed number of trials, that she only shoots 12 arrows. So yes, this is a binomial random variable. So this sample size is more than 10% of the population. This is not a condition for a binomial random variable. And the sample size is not large enough. That is also not a condition for a binomial random variable. Question 5. Airlines often sell slightly more seats than they have available as they know that only 95% of ticket holders show up. The other 5% of passengers cancel their flight at the last minute. A certain plane has 137 seats. An airline wants to know how often too many people will show up if they sell 140 tickets. So they want the standard deviation for the number of passengers that show up. So the most important thing about this question is we need to recognize it's a binomial variable. So a person either shows up or they don't. There's 140 tickets. That's a fixed number of trials. And that chance of success, the chance of showing up, is the same each time. It's 95%. So we're going to use the standard deviation of the binomial formula, the square root of n times p times q, which is right here. So I'm going to do the square root of n, which is 140 people, times p, the percentage of showing up, 0.95, times q, which is just 1 minus p, which is 0.05. And we see that that square root is 2.57. 5788. So if you're tempted and you're confused, when do I use the square root of p times q divided by n? If I had done the square root of p times q divided by n in this problem, let's see what it would have been. 0.95 times 0.05 divided by 140. If you had done that, that is the standard deviation of the sample proportion. So that number, this 0.018, that is the standard deviation of this proportion, this 95%. So you're not looking at the standard deviation of the proportion, you're looking at the standard deviation of the number of passengers. And that's why you use the square root of n times p times q rather than p times q divided by n. Question 6. Instead of letter grades, the university uses grade points to calculate GPAs. In a recent semester, Dr. G assigned grades using the following distribution. So it gives us this distribution. It says find the standard deviation of the grade point distribution. So this is the process for expected value and expected standard deviation that we have to go through, and it involves creating two vectors, which are just lists of numbers. So first I'm just going to create a vector of all of these grade points, just 4, 3, 2, and 1. I'm going to create a list of them, and I'm going to call it GP. You can call it whatever you want. Then I'm going to make a list or a vector of these probabilities, 0.3, 0.4, 0.2, and 0.1. It's important that these match up. So the first one here is the first one here, the second one's match up, the third one's match up, the fourth one's match up. So I'll create that vector. Our expected value, or our average or our mean, is basically the weighted average. So it's 4 times 0.3 plus 3 times 0.4 plus 2 times 0.1 plus 1 times 0.1. And we add those all up. And that's what we do with this code. This expected value, EX, is the sum of 4 times 0.3 times 0.4 plus 2 times 0.2 plus 1 times 0.1. And it's exactly like doing that sum product function in Excel. If you've ever used that, it does the exact same thing. So if I want to see what the expected value is, it's 2.9. So basically the average GPA is a 2.9. Now we have to figure out what the standard deviation is. So I want to figure out the variance, or what I call right here, the squared deviation, SQDev, of each grade point. So I'm going to do each grade point, so 4 minus 2.9 squared, 3 minus 2.9 squared, 2 minus 2.9 squared, and 1 minus 2.9 squared. So basically that is each grade point's variance from the mean. It's deviation from the mean squared. So that's the squared deviations. That's just a list of those squared deviations. And now I have to multiply each of those squared deviations times their probabilities, which is this list that I created earlier. I'm going to add them all up to get the variance. So the variance, see over here, is 0.89. Take the square root of the variance to get the standard deviation. If you have specific questions about this, come see us in office hours because it can be kind of confusing. And just write this progression of code down. And this is the same progression you'll use whenever you have probability distributions and you need to figure out what the standard deviation is. Question 7. At the grocery store, you decide to buy a 5-pound bag of apples and a 5-pound bag of potatoes. Although the bags of apples are labeled 5 pounds, the weights vary, actually vary randomly according to a normal distribution, mean of 5, standard deviation of 8. The bags of potatoes also vary. Their weights are normally distributed with a mean of 5 pounds and a standard deviation of 1.5. After you pick up the 2 bags of produce, you're not buying anything else. So we want the weight distribution of your groceries in total. So if I add 2 normal random variables together, the sum of them is going to be normally distributed. That's just a rule. So we rule out this first option. It has to be normally distributed because both of them are normally distributed. So we calculate the expected mean by just adding those 2 means together, 5 plus 5, and we get the mean of 10. To calculate the standard deviation, we can't just add the 2 standard deviations together. We have to square them and add the variances together. Find the total variance, then square root that variance. It works similar to the Pythagorean theorem from geometry. So I have to do the first standard deviation, 0.8 squared, plus the other standard deviation, 1.5 squared. Add those together, and then square root that to get the standard deviation. And we see that it's 1.7. Another thing that's important that you should remember about this is that the means, in order to add 2 means, the variables do not have to be independent. In order to add the standard deviations and the variances, in order to combine those, we have to assume that the weights of apples and the weights of the potatoes are independent. So to add the means, it doesn't matter, but to add the variances or the standard deviations, it does matter. They do have to be independent. So we got mean 10, standard deviation. Question 8. UT wants to survey a sample of its 50,000 students to determine what fraction of the student body would prefer to cancel classes during the entire week of Thanksgiving and start the semester 2 days earlier. However, they would like to be 95% confident that their sample estimate is between 0.1% of the actual percentage of students. So we need to figure out the sample size. So that equation for margin of error that you learn is margin of error equals z star times the square root of PQ divided by N. So the margin of error is our z star, or our critical value, times the square root of PQ divided by N. When we're solving for what sample size is necessary, we just rearrange that equation into this, line 42. That's what I rearranged line 40 into line 42. Also, if P is not given, you always need to use the worst possible p that's going to give you the biggest sample size number. So we use 0.5 if p is not given. So I'm going to multiply p, which was not given, so I'm going to use 0.5, times 1 minus p, which is also 0.5, times my z star divided by my margin of error squared. So let's talk about z star for a second. Z star, or the critical value, is the point on the normal distribution, is the value on the normal distribution that corresponds to that confidence level. So this code I have right here, this Q-norm function, is going to give me the Z star for a 95% confidence interval. So if I wanted this to actually be a 90% confidence interval, you would just change this to 0.9. If you wanted it to be a 99% confidence interval, you would change it to 0.99. So this is a 95% confidence interval, so that's why I have this 1 minus 0.995 in here. If you want to know why this is like this, give me an email or come to the review session and I can go more in depth. It's kind of difficult to without a whiteboard or a piece of paper in front of me. And then we're going to divide by the margin of error, which is 0.1%. And we get n is 960,364. So we need to sample 960,000 students in order to get 0.1% margin of error, 95% confidence. That's not possible. The question says only 50,000 students are at UT, so it's not possible to gain that level of precision. Question 9. The scores in the file grades are from a previous semester. The scores are blank. So let's grades. So we see there's student ID numbers just assigned randomly and grades. So in order to see whether they're skewed or not, let's look at a histogram first. So this histogram to me looks pretty normal. But if this didn't look normal enough to you, let's check a normal QQ plot, which is made using the function QQ-norm. We look at this, it's supposed to be a straight line. This looks pretty straight. It's a little bit curved at the ends, but we can make a straight line go through it if you want. And it's this AB line with the mean and the standard deviation to be the slope and the intercept. And you see that the straight line goes very well through it. So let's say this is pretty normal to me. Figured that just from the histogram. You could have also looked at skewness and kurtosis, but the histogram was sufficient to see that this was approximately normal. And the professors aren't trying to trick you with the questions. It'll be obvious whether it's skewed or normal. Question 10. Based on a random sample of 120 monkeys, a 95% confidence interval for the proportion that were assigned to research studies is between 0.67 and 0.83. Which of the following is true? So let's go through all of these. If we used a different confidence level, the interval would not be symmetric about the sample proportion. So our confidence interval is always symmetric about our sample proportion. We have the sample proportion in the middle, and we add our margin of error on one side, and we subtract the margin of error on the other side. So no matter what the confidence level is, the sample proportion number is always in the middle. This one, 95 of the sampled monkeys were assigned to research studies. So this is talking about the number of sampled monkeys. Our confidence interval does not tell us anything about individual sampled monkeys. It tells us about the percentage of samples. So let me repeat myself. So if I repeatedly took samples of 120 monkeys for the rest of time, 95% of those samples would contain the true proportion of monkeys assigned to studies. So that 95% number doesn't tell me about the sample. It's going to tell me about the true proportion. So that's why this third choice is wrong. D, the margin of error for the confidence interval is 0.16. So the margin of error is not just the difference between these two numbers, which is 0.16, it's the difference between these numbers divided by 2. Because because the sample proportion is in the middle, and I add a margin of error on each side. So it's 0.83 minus 0.67 divided by 2, so it's actually 0.08. Last option, a larger sample size will give us a wider confidence interval. A larger sample size is actually going to give us more information so we can be more specific in our predictions, in our confidence. We have more data, more confidence. More confidence actually yields a narrower confidence interval. So a larger sample size is going to give us a narrower confidence interval. The other relationship that it can be confusing is a higher confidence level is going to give us a wider confidence interval. But that one isn't mentioned here. A larger sample size is going to give us a narrower confidence interval. So none of these are true. Question number 11. Airlines often sell slightly more seats than they have available, as they know only 95% of ticket holders show up. So this is the same question as earlier, and it's asking, can they use the normal approximation for the binomial to calculate the appropriate probability? So we talked about binomial trials earlier. As I get more and more binomial trials, eventually the distribution is going to look more and more normal. So in order to do the normal approximation of the binomial, I have to have enough data that is going to show that it looks normal. So that condition is this n times p and n times q must be greater than 10. This is for normal approximation of binomial. So it's when I have enough trials that the binomial distribution is going to look normal. So let's check. I have 140 times this 5%, and we see that is 7. 7 is less than 10. So the success failure condition is violated. So this is called the success failure condition. And let me write that in this code. So the normal approximation for the binomial, there still have to be 2 possible outcomes because it still has to be a binomial. The binomial conditions don't go away. The sample size is not large enough. We know that from this. They can't use it because the success failure condition is violated. Question 12. 20th Century Fox claimed that half of all college students have seen the movie Hidden Figures. From a simple random sample of 200 UT students, you find that 48% have seen the movie Hidden Figures. The 95% confidence interval is 41% to 55%. Can you reject the claim that half of UT students have seen Hidden Figures? All of these options are talking about p-value. And we were given a confidence interval. It's important to recognize this 95% confidence interval corresponds to 0.05 p-value. So if this 50%, the claim, is inside the confidence interval, that means it's possible. So because 50% is in this interval, it's likely that the true proportion is 50%. So can I reject the claim? No, I can't reject it because 50% is in the interval. So we know we can't reject the claim. Now we need to decide, okay, is the p-value going to be less than 0.05 or more than 0.05? So if we know we fail to reject, then you make the transition, okay, fail to reject is if the p-value is big. So I cannot reject, I fail to reject because the p-value will be greater than 0.05. Question 13. A researcher wants to estimate a 70% confidence interval for a proportion. What is the value of z star, the critical value, that the researcher should use to construct this interval? So now we're going back to that question where we used Q-norm earlier, and we were trying to figure out what's the sample size. So we're going to go more in depth on this question about what does Q-norm do, and what do you need to do to find the z star. So this code in line 81 is the exact same format as this code that I had in line 44. And it's telling me the z star. So if you just want to use this line of code and plug in your confidence interval right here, go for it. It's going to give you the right z star. We're just going to go more in depth explaining what this is doing. So our Q-norm function is when we give it a probability and it gives us a quantity or a number. So we give it a percentage, gives us quantity. P-norm, we give it a quantity, gives us a percentage. So Q gives quantity. But we have to tell it the percentile. So when we think about a 70% confidence interval, that's talking about the middle 70%, which means there's going to be 15% below and 15% above. And we need to tell Q-norm those boundaries of the middle 70%. You can't tell Q-norm 0.7. You have to tell it the boundaries. So we know there's 15% on each side. So I can tell Q-norm, okay, I want the bottom 15% plus the middle 70%, Q-norm of 0.85, which is 1.03. Or I can tell Q-norm, I just want that lower border, 15%, and that's going to give you just the negative of that number. If you don't want to do that, adding the tails in your head, use line 81 and plug in whatever confidence level you want right there. Because what this is doing is it's doing 1 minus 0.7, which is 0.3, 0.3 divided by 2, which is 0.15, and then it's doing 1 minus 0.15 to get 0.5. It's just doing the calculation from 81 to 84 for you. So whatever you're more comfortable with, that's what you do. You get the same answer using all three methods. Question 14. Some graduate school's courses, oh my goodness, I'm so sorry. I forgot to say this in the last question. So Q-norm, I taught you, you were taught, we put value, we put mean, and we put SD. Q-norm defaults to a mean of 0 and a standard deviation of 1. So I put, Q-norm, we put a percentile, mean, and standard deviation. So we're giving Q-norm just a percentile here. Q-norm always defaults to the normal distribution, the mean of 0 and the standard deviation of 1. So if you're looking for your critical value or your z-star, you just need to put the percentile. But if you want to put the mean and standard deviation, it's going to be that regular normal distribution, mean of 0, standard deviation of 1, and you get the exact same answer. It just defaults to a mean of 0 and a standard deviation of 1. So that's an update about how Q-norm works. Okay, back to question 14. When we're back in Q-norm, and because we're not looking for a critical value, we have our mean and standard deviation back as it regularly is in Q-norm. Okay, back to question 14. Some graduate school's courses pass the top 90% of a class and give a high pass to the top 10%, gives warnings to the bottom 10%. If students receive too many warnings, there are academic consequences. In a marketing class, the average is 634, the standard deviation is 42. What's the lowest grade with which you can pass this class? So we're seeing what grade, what quantity we can to be at the borderline of that bottom 10%. So I'm going to put that value 10%, bottom 10%, median 34, standard deviation of 42, and the lowest grade is 580.175. Question 15. The state of Texas is putting referendum number 123456 on the ballot this fall. The local news station ran a poll to test voters' opinions in voting for or against the referendum. There are around 15 million voters in Texas. The analyst was able to get phone numbers for 100,000 voters and decided to hire a crew and call 20,000 of these numbers. Only 500 people answered, and 274 supported the referendum. And this is a definition question. It gives you a lot of numbers, and it says, what is the size of the sampling frame? Definition of a sampling frame is the list of people forming a population from which a sample is taken. So our population is 15 million. The list of people forming the population that we have is 100,000. Now, we called 20,000. Those are people that were sampled but did not respond. And our actual sample is 500. So the sampling frame is 100,000. Question 16. 40% of the employees in a local firm are women. You decide whether to see the same proportion of executive level positions are filled by women. Of the 43 people in executive positions, 13 are women. You assume that 43 executives are a random sample of the 870 employees and conduct the hypothesis test. You find that the p-value for the test is equal to blank. Okay, so success failure condition. We see that this 0.4 times 0.43 is 17.2. 17.2 is greater than 10, so that success failure condition is satisfied. Also, 43 women that were sampled is less than 10%. Of the 870, 43 is less than 87, so that is also satisfied. So we're going to do our hypothesis test, which is this z-test.p function. And in our z-test.p, we put our p hat, which is our sample proportion. We put our n, our sample size, and we put p0, which is the proportion of the entire population that we're trying to test, that we think it is. So we put our p, which is the sample proportion, which is 13 out of 43. Our sample size was 43. And the proportion we're trying to test is 0.4. You run that, and we get a bunch of different numbers. You get a test statistic, you get a lower p-value, you get an upper p-value, and you get a two-sided p-value. So you need to decide whether this test was asking for whether the percent of women is lower than 40%, greater than 40%, or just different from 40%. So this question was seeing whether the same proportion are filled by women. So it wasn't asking about a specific side, greater than or less than. It was asking just whether they're different. So when it's asking just whether they're different, you use the two-sided p-value, which is this number. It's asking if they're different, use the two-sided p-value, which is 0.191. Question number 17. This is also a definition question. A new test to detect the strep virus is generally accurate, but sometimes reports strep throat when the strep virus isn't present, and sometimes reports no strep throat when the strep virus is present. The null hypothesis is that the strep virus is not present. When a test reports the strep virus is present, when it isn't actually present, this is an example of blank. So you need to know the definitions of all of these things. Sampling error is when I sample badly. So it's when my sample is unrepresentative. This wasn't about sampling, so it's not sampling error. Standard error is the standard deviation of the sample. Standard error is the standard deviation of the sample. It's natural variation. It's not really error. Dr. Maliski calls it sampling variability as a better name because it's not really error. It's just the variation of the sample. This wasn't actually talking about a sample, so those two are ruled out. Now we need to know the difference between type 1 and type 2 errors, which I would just write down on your cheat sheet, have them on the paper so you can reference them because they are kind of confusing to memorize. Type 1 is a false positive. It's the incorrect rejection of a true null hypothesis. So it rejected the null hypothesis, even though the null hypothesis is true. So that's saying the null hypothesis is not present, but we said it was. The strep virus is not present, but we said it was. Type 2 is a false negative, incorrectly retaining a false null. That means we say strep is not present, but it actually is. For this question, I think it's easier to think of this as a false positive. It says it's present, but it's not. That's a false positive. This is a type 1 error. Just write the definitions down, learn how to read them, and learn how to think about them in your own way so you know how to interpret those. Okay, question 18. This is another conceptual question. Trader Joe's is willing to sponsor an advertisement on radio only if the station can show more than 15% of Austin's residents listen to the station. The radio station will survey 1,100 Austin residents. Which hypotheses should they test? Okay, our null hypothesis is H0, and that's always going to be that P equals 0. P equals something. So our null hypothesis always has to be H0 equals something. So this first option, H0 is a less than. That doesn't work. The null is a not equal to. That doesn't work. This is a greater than for the null. That doesn't work. That only leaves us with this based on that first rule. The other thing you needed to look at was our alternate hypothesis is more than 15%. So we're testing P is greater than 0.15. So there are two major things that help you rule out all of these answers because this alternate is equal to, this alternate is equal to, this alternate is equal to. This is the only one that works for both of those options, for both of those ways you could have thought about the question. Question 19. X is a randomly distributed, normally distributed variable with 500 mean and 100 standard deviation. What's the chance that it will take a value between 600 and 700? So we're looking for probabilities, and it gives us values. We want probabilities, so we're going to use p-norm. And p-norm always gives me the percentage to the left of that value, the chance that it will be less than that value. So if I want the between percentage, I need to do all of the percentages less than 700 minus all the percentages less than 600, subtract those two in order to get the middle percentage. That's how we set this up. P-norm, we always put our value, comma mean, comma standard deviation. I did that for both of those two. And we get that probability is 0.136. 136. Question 20. According to a candy industry website, 10% of M&Ms are orange. If you find that in a randomly filled and selected 500 M&M bag, 12% are orange, is this convincing evidence that at the 5% level of significance, that the true proportion of orange M&Ms is greater than 10%? So we're doing a hypothesis test. So we have that convenient function called ztest.p. Let's use that. ztest.p. Let's remember what we put in there. And it says over here, you put p hat, which is the one we're testing, which is our sample proportion. P hat's our sample proportion, which is 12%. Then we put n, which is the sample size, 500, and then we put the proportion we're testing, which is this 0.1, which it gave us in this test. Little description. So I'm going to run that ztest.p. Now we need to decide which of these values I need to look at. And it said we're testing whether p is greater than 0.1. So that's the upper, the greater than. So I'm going to use the p-value. And that is 0.06. Question 21. Austin, Texas has had an average rainfall of 32.15 inches with a standard deviation of 8.33 inches. If the rainfall distribution is normally distributed, what's the probability that the rainfall in 2017 will be exactly equal to 40 inches? So you learned about this in class. We can't take the probability of a continuous random variable being exactly equal to something. The probability that it's going to be exactly equal to 40.0 is 0 because it's a continuous variable. It's like taking the integral, the area under the curve of a single point. We can't do that. So the probability is going to equal 0. If it asks you what's the probability that the rainfall will be less than 40 inches, you could do your regular p-norm. If it asked the probability that it's going to be greater than 40 inches, you could do your 1 minus p-norm. If it asked you the probability that it's between two values, you could do the p-norm minus the other p-norm. But exactly equal, that probability is always going to be 0 for normally distributed. Question number 22. A student group did a poll of 50 UT students and found that 40% of those polled believe that the UT football team will make a bowl game this year with a margin of error of 6.8%. Which of the following changes to the poll would increase the margin of error if the percentage of poll respondents that believe UT would go to a bowl game remain the same? So, population size does not matter with our margin of error. The only thing that matters is the sample size. Remember, our margin of error equals our z star times the square root of n times, p times q divided by n. So what matters is this proportion, and it said the proportion, the percentage stayed the same. The P and Q stayed the same. So those stayed the same. So N would affect margin of error, and Z star would affect margin of error. Remember, Z star is that confidence level. So none of these options are talking about confidence level. So that's not going to change the margin of error. Now, N is the other thing that could change the margin of error. So what is going to increase the margin of error, make it more error. So if I decrease the sample size, I'm dividing by a smaller number, so my margin of error is going to go up. If I increase the sample size, I'm dividing by a bigger number, so my margin of error is going to go down. So these first two are talking about the whole population. So this taking a sample of Austin residents versus UT students, this doesn't change the margin of error. Those don't have anything to do with this margin of error formula. We don't know whether it's going to increase or decrease the margin of error. It might change it, but knowing that those P and Q have stayed the same, then it's still the same sample size. It's still the same Z star. It's still the same P and Q. It's still 50 students, 50 people are sampled. So that's why those are not affecting margin of error, because the sample size is still the same. If I decrease the sample size, the margin of error is going to go up. If I increase the sample size, the margin of error is going to go down, holding those other things constant. Question 23 is also conceptual. Suppose you collect information for the students at Stephen F. Austin High School. Which of the following random variables are discrete? So discrete means that a variable can take on any value between two specific values. So if I say for shoe size 6 and shoe size 7, can you have a shoe size of 6.26437? No, that's a discrete variable because, excuse me, I wrote this wrong in the script. Let me change it really quick. So continuous means they can take on any value. Cannot. So they cannot, so they're discrete. Grade level. So if I have two specific values like grade level 8 and grade level 9, can I have a grade level of 8.7374? No. That is an also discrete variable. Now you think GPA. Can I have a GPA between 3.6 and 3.7? Yep. I can have a GPA of 3.61111111 repeating. So GPA is continuous. Similarly, height can take on any value between 5.6 and 5.7. Take on any decimal value. It might be hard to measure that exact value, but it can take on any value. Similarly, travel time may be hard to measure, but it can take on any value between 15 minutes and 16 minutes, down to all of those milliseconds. It might be hard to measure, but it is continuous. So those two discrete are shoe size and grade level. And that is all for the practice test. We're having the review session on Thursday. If you have any other questions, email the TAs or your professor, and good luck on your exam.